Right. So this week, Nicolas Allen Smoot is speaking, and he's talking about partition congruences and the localization method.
Well, thank you very much. This may... Thanks for the introduction, and thanks for the invitation. I really appreciate it. I'm sure everyone feels a little bit isolated last few months. And last few months for me in particular, I've just been writing up my thesis and doing job applications and stuff like that. So I haven't really gotten to do much actual math or to talk to actual people about math. So I very much appreciate you guys going to the trouble of setting this all up. This will be, so I want to talk about something I've been working on at Risk for the last, actually almost last year. Last September is when I started working on this little problem. And it's got some peculiarities in the theory of partition congruences, proving families of partition congruences. I found this new set of techniques that might come in handy for other kinds of problems. Oh, we'll just jump in. So, okay, section 1, what is a partition? No, we're not doing. I assume everyone knows what a partition is, right? Like and what the partition function is. Okay, that's good. So, well, I will start out with this because it's sort of the ultimate motivating example that pretty much everyone should know about right now. That this is the first really deep arithmetic information that we got about the integer partition function. Ramanujan got the first few cases, p of 5n plus 4, 7n plus 5, 11n plus 6, and then he was able to guess these families of congruences, these infinite families of congruences, which are very remarkable the more you look at them. And they're not exactly true. The powers of 5 and 11 are exactly true, but the powers of 7 are even more interesting. They have this peculiar little wrinkle here, right? But this was first conjectured about 100 years ago, and it's been like we've managed to get a lot of new results and interesting ideas out of these families of congruences in the past century. Watson was the first person to publish a proof for the powers of 5 and 7, although I think the historical consensus more or less is that Ramanujan knew how to do it for powers of 5. Although in typical Ramanujan fashion, he skipped lots of steps and didn't show all of his work, but he had the basic idea. He certainly didn't know how to do the powers of 11. Neither did Watson. Atkin did that in 1967, I think, which is something like 30 years after Watson's work for powers of 5 and 7. And I want to walk through just the basic way these are proved. I can't go into all the details, but just the basic idea. So we start off with this identity here, which is justifiably admired. It's one of Ramanujan's finest pieces of work. Everyone knows what the Q Risen factorial is, right? The Q Pochhammer. I can write that up on the board if needed. It's just shorthand for an infinite product. So, okay, this very lovely identity gives us the fact that p of 5n plus 4 is divisible by 5. And we can kind of normalize the identity a little bit. If I multiply on both sides by this little prefactor, then look on the right, and an extra power of q, on the right-hand side, you may know that with the right change of variable, that's a modular function over gamma 0, 5. It's a to 5 tau to the 6 over a to tau to the 6. And this is a good way of proving the very first case of Ramanujan's partition congruence family for powers of 5. If I want the second one, right, you notice it has a very, very similar form. It's just a bit more complicated. So it's just a polynomial in what is effectively this object here on the right-hand side for the case alpha equals 1. It's just a polynomial in that with integer coefficients. And I've got 5 squared in each coefficient. So p of 25n plus 24 is divisible by 25. And you can probably guess the general pattern. If I let t equal this product here, again, it's just an eta quotient. Then I can write the generating function for p of 5n plus 4 with the appropriate prefactor, and for p of 5 squared n plus 24 as just polynomials in t. And I can just look at the coefficients of these polynomials. And t, of course, expands into an integer power series, so we don't have to worry about it. And more generally, if I define the slightly normalized generating functions for each of these cases, say L sub alpha, then these generating functions can be written as polynomials, integer polynomials in our T. And not only that, but each L alpha plus 1 is U of L alpha, where U is a certain kind of linear operator. And I won't go into what these operators are, but they're pretty straightforward. In this case, it's just an alternating sequence of relatively well-defined linear operators. So you know how to go from one L alpha to the next. So you can probably sense there's an induction argument in here, improving them. So very, very, very quick assessment of what you basically do. So you have each L alpha as an integer polynomial in T. You know how to get each L alpha from the previous L alpha by applying the appropriate linear operator, because it's linear. If what you have is already divisible by power of 5, you can pull that out and examine what's left. And we know that L1 is 5t. So you can basically show for every alpha, U alpha of L alpha over 5 to the alpha is an integer polynomial that's divisible by 5. So from going from L alpha to L alpha plus 1, we pick up an extra power of 5. And that's how you do the proof. Now, I went through it fairly quickly, but that's the basic idea. The big thing I want to point out is we're working with an integer polynomial ring, C of t in this case, right? There's that very, very nice simple algebraic structure. Right? Now, the same technique works for powers of 7. Okay, you have to be a little bit more careful with how the powers increase, but it's not that big a deal. This does not work exactly for powers of 11. It almost does, like in a way it kind of does, and we'll get to it, but this overall technique doesn't quite work. So that's the Ramanujan's standard partition congruence families. Now I want to do just a little bit slightly more abstract theory, although I suspect most people here already know about this stuff. If you don't, just ask me a question, because I'll blow through it kind of quickly. I'm defining gamma 0 n as just your congruence subgroup. So it's just all of your matrices in the special linear group where your lower left component's divisible by some n. And n's a natural number, right? And now let h hat be the upper half complex plane in union with the rational numbers and infinity. And you can think of infinity in this case, well, you can think of it just like 1 over 0. In this case, that's a fairly okay way of thinking about it. So we can define a group action on h hat by gamma 0 n. Right? And everyone knows this. A, B, C, T applies to tau. It's just A tau plus B over C tau plus D. And I can define an orbit of a given tau as just the set of all gamma tau for gamma and gamma 0 n. And with this in mind, you can define the classical modular curves. These are just the set of all orbits of gamma 0 n applied to h hat. Okay. And it's not obvious by the way you look at this, but the idea is that x0n, the modular curves, are Riemann surfaces, compact Riemann surfaces, in fact. They're very, very well-behaved objects. You can do analysis on them. You can study functions on them in a very, very nice way. And a lot of the stuff from complex analysis goes to these modular curves in some form or other, right, which makes them very useful to study. And in particular, the rational numbers and a point infinity, right, can be represented as a set partition of a finite number of orbits. And the orbits are called the cusps of the modular curve. Questions so far? No? Okay, I didn't think so. So, okay, very quick definition of modular function, at least how I'm going to define a modular function over gamma 0 n. Okay, I have a holomorphic function f over h, and it's modular if I take any two elements in h and they're in the same orbit, then the output's the same. So f of tau 1 is f of tau 2. And moreover, and this is how f is going to behave along the rational numbers and at infinity. If I take any element in the special linear group, I can look at f of a tau plus b over c tau plus d. I can write it out as this series here, alpha gamma n q to this fractional power to the nth power. Now, alpha n is just a complex number. We're starting, notice that there is a lower bound how we start. So n gamma is an integer. It can be positive, it could be 0, it could be negative, right? And the idea is, if you want to think about it, you can imagine tau here on the left-hand side going to infinity, or if you like to I infinity. And then we know that in the limit, this goes to a over c. And you can imagine if tau goes to I infinity, q in effect goes to 0. So you can look over here, and if n gamma is positive, then you can, and this whole thing will seem to go to 0. And you can say that the function has a 0 at the rational number a over c. And if it's negative, it has a pole. So with this change of variable, it's kind of convenient to think about. So now, the connection of this to the partition congruence families is that for each of these partition congruence families, we can associate a certain compact Riemann surface. You can probably guess why. Those L alphas that I showed you earlier, they're modular functions, and they correspond to functions over a given modular curve. So the congruence family for powers of 5 is associated with x0, 5. And for powers of 7 and 11, the very natural modular curves you expect. And okay, so I said that these surfaces are interesting for analytic purposes. They're also interesting for topological purposes. So each of these surfaces has a certain unique number. It's called the genus. It's just the number of holes in the surface, or if you like, handles in the surface, right? So the genus of x0, 1, 5, and 7 is 0. These are just topologically spheres. And the genus is, say, x0, 11, or say x0, 20 is 1. These are donuts, or coffee mugs, as everyone will tell you. Okay, so why is this important? Well, here's the, and this isn't the complete Weierstrass Gap Theorem, actually. I'm only giving you like a shorthand version of it. The idea is if I take a compact Riemann surface X, and I have a function f that's holomorphic over X. First of all, it can't be holomorphic over all of X. So it has to have a pole at least somewhere. But we can imagine having a function that's holomorphic over all of X except for a single spot on X, single point. And we can say f has a pole at that point. Okay. Then the order of our function f at that point can be any negative integer we want with exactly g exceptions. G is the genus. So for example, right, I will work with, say, x0, 5. I can take the function that we already looked at earlier, t. I'll look at 1 over t because it's a little bit easier. So 1 over t has this nice integer power series expansion in q. Notice it has a pole when q goes to 0, or effectively when tau goes to infinity. And it's a pole of order 1 or negative 1, right? And t will induce a function defined on the modular curve, very, very naturally. And now if you think about it, 1 over t, okay, it has order negative 1. If I want a function that's holomorphic over all of x0, 5 except for the point at infinity that has order 2, well, I'll just square 1 over t. Or I could cube it to get a degree, a function with order negative 3. And in fact, I can get any order I want, any negative number. So there are 0 exceptions, and sure enough, the genus is 0. Right? That's a trivial example, but simple enough. And then on the other hand, if I were working over the curve of level 20, working over gamma 0, 20, I have 2 examples here, modular functions, holomorphic over all of x0, 20, or they induce functions that are holomorphic over all of x0, 20, except again for q equals 0 or tau equals infinity. And you'll notice their orders are negative 2 and negative 3. And of course, combinations of negative 2 and negative 3 will give you any negative integer you want, with a single exception, the exception being negative 1. And sure enough, you can't find a modular function that's holomorphic everywhere except at infinity with order negative 1. So we have a single exception, and the genus is 1 for single exception. So this is useful because it gives us some restrictions to the analytic functions we're allowed to work with, and the algebraic structure of the spaces of those functions. In fact, that's the big thing I want to look at here. If I let MC of gamma 0 n, if I let this be the space of modular functions over gamma 0 n, with a pole only at one cusp, C, so C is either a rational number or infinity, then if the genus of the surface is 0, then MC of gamma 0 n is isomorphic to just the polynomial ring over the complex numbers. I can find a function t such as the space is just CT. If the genus is 1, on the other hand, that's not true. Instead, the space is isomorphic to a CX module, a free CX module, and the rank is 2. Excuse me. You can find functions, in this case I'm calling them t and rho, right? Now, why is this important? Well, in the case of the partition numbers for powers of 5 and 7, this first corollary applies. So that's the space of functions that we're working over, in effect. In the case of powers of 11, it's no longer that simple. At best, you're working with a space that looks like this here. It's a CX module of rank 2. Very often, it's worse than that. So, for example, if you guys know anything about the Andrews-Sellers conjecture, it was proved by my advisor, Peter Paula and Sylvie Radu. They actually have to deal with a pair of rank 2 CX modules, bouncing back and forth to account for certain other complexities. But you see, when the rank of the space of functions that you're looking at goes up like that, then that induces all sorts of complications. So in general, the genus of your underlying Riemann surface plays a huge role in how complicated the proof of a given family of congruences is going to get. If the genus goes up, you can expect the proof is going to get more complex. And you would expect the genus is 0, we more or less understand the proof. Ramanujan basically understood it, and Watson understood it. And we understand the modular function machinery underneath it, and it doesn't seem that complicated. In fact, a lot of proofs about partition congruence families, when the genus is 0, barely touch on modular function stuff at all. Ramanujan probably didn't think too much about it. It's so simple, you don't really have to pay too much attention to the modularity stuff. So I want to talk about a family of congruences that was discovered a couple of years ago by Yifan Yang and Liquan Wang that has, well, a couple of really surprising properties. And the way I'm going to do it is I'm going to start with the normalized weight 2 Eisenstein series, which I got right here on the screen, E2 of tau. Now you may remember E2 of tau is not really all that well behaved as a function, but you look down here, 2E2 of 2 tau minus E2 of tau, that's a nice function. In fact, it's a modular form and relatively well behaved. So I'm going to find Cn as the coefficient of this function, this generating function. Now, Wang and Yang were able to give a proof. I don't actually know about this current status of their paper, but they gave a proof that this C of n function has a family of congruences for powers of 5. That if 12 delta alpha is 1 mod 5 to the alpha, then C of this number is divisible by 5 to the alpha. And the reason this is interesting is that it turns out using this, you can prove that, of course, there's a corresponding congruence family for powers of 5 over the SPT analog of the omega function. Now, what this means, I won't go into too much detail. It's still got time. But the omega function, the omega mod theta function, has, if you don't know, it has the coefficients of the function have a combinatorial interpretation, a partition theoretic interpretation. I think it's the number of partitions of n in which all the odd parts are less than or equal to twice the smallest part. One of those kinds of partition interpretations. And you can look at just the total number of such partitions and you can develop an SVT function, a smallest parts counting function. And when you do this, you find that there's this neat congruence family. Now, for powers of 5. And that's implied by this theorem here for this C of n function. So just to walk through how this is roughly proven, it looks very similar to how you would start a proof for congruence families for powers of, say, 5, what I showed a little earlier. I can find these functions L alpha. They're just slightly normalized generating functions for each case. For example, L1 has this q to the 10 prefactor in front, and it's just the generating function for c of 5n plus 3. And the game, obviously, is to show that each L alpha is an integer power series, right? That's where the coefficients are divisible by 5 to the alpha. Now, what Wang and Yang originally did, and I'll show, for example, their first key example here, is they write L1 like this here. Now, a few things to pick apart here. T and rho are just eta quotients. They're modular functions. They have integer power series expansions, relatively well behaved. F in this case is a modular form with a constant term 1 over, and all of this is over gamma 0, 10. So you may notice that L1, the way L1 is defined here is it's not really a modular function. It's a, if you like, it's a weight 2 weakly holomorphic modular form of weight 2. So, and that's the main reason of that is that this F function here is a little cumbersome to handle. So in principle, we could go back here and define each of these L alphas with the F underneath each of the prefactors. That would just be a little bit cumbersome. So we just put it here. But it has, the F doesn't interfere with any of our calculations. It's just sort of along for the ride. Okay. And you'll notice, as a result, I can kind of ignore the F, and I look here, I've got divisibility by 5, 5, 5, 5, 5. So we have divisibility by 5. So you can tell L1 is divisible by 5. More generally, they prove this, that L alpha divided by 5 to the alpha times F is in this rank 2 ZX module, ZT plus rho ZT. And again, this is characteristic of the method. I mean, Paolo and Radu used, although it's been used in modified forms in the past, right, for proving congruence families when the associated modular curve has genus 1. Okay, now, any questions so far? All right, so here's the key weird feature. All this is done over gamma 0, 10. The functions are done over gamma 0, 10. So the corresponding modular curve is x 0, 10. Right. And the genus of x 0, 10 is 0. So I noticed this looking over Wang and Yang's preprint about a year ago, and that immediately sent up a red flag, because in a sense what they're doing, their method, is acting as if the modular curve has genus 1 when it's actually got genus 0. And that immediately raises questions. Why are they doing this? Why are they treating a sphere like a donut? Why are they using these slightly more advanced techniques? And they shouldn't have to. You should be able to write these L functions just in terms of polynomials in some T. That should be much easier. Why aren't they doing this? And so I immediately thought, well, I'll do it. How hard can it be? Turns out it can be hard. So first attempt. And I'm looking at the space of modular functions over gamma 0, 10 with a pole only at 0. Okay. This is a polynomial ring, Cx, and x is this eta quotient you see here. Relatively simple looking eta quotient. And I'm choosing this function x for a reason. So this x can be constructed very easily. I work at RISC. I do a lot of computational math. I have a lot of algorithmic machinery for this. Like you can very, very easily construct a function x like this, and you can choose it so it will have zeros that will overpower the poles of L1 over F. You can show without too much difficulty that L1 over F, you can write all this in terms of Eisenstein series, is holomorphic over H, but it will have poles at certain spots in the rational numbers at infinity, at the cusps. And X has zeros, positive order, at the poles of L1 over F. So if I raise X to a high enough power, in this case 3, then X cubed times L1 over F is a modular function with a pole only at one spot at 0. And therefore I can write as a polynomial in X. So it's fairly straightforward now. I just divide through by X, right? I can just write L alpha over F as a polynomial in X and 1 over X. And it turns out you can do this for every L alpha, not just L1. So it's much more simple. Why are we dealing with this this weird identity with two different functions, a t and rho? Let's just do an x. Just write it all in terms of x, and it'll be much nicer. Here's the problem. So I should emphasize this is the only x that we can really choose, that we have a limited number of eta quotients that we can choose from. And when you choose this x, we end up in trouble. So you may notice, first of all, the coefficients aren't integers. That's bad. Second of all, the numerators aren't divisible by 5. That's also bad. And what's worse is that the denominators are, in effect, 5 to the infinity, just massive powers of 5 in the one spot we don't want them. I want to show that L1 is divisible by 5. Well, first of all, I have to show that this whole mess combined is going to cancel out the 625 on bottom. That's not helpful. So this clearly doesn't work. And for computational reasons, you can show without too much trouble that this function x, this eta quotient, is really the only one that you can find. You can get a bigger eta quotient in a sense that will cancel out all the poles of L1, but the order of that function is going to go up, and next thing you know, you can't just write everything as a polynomial in that function. It's no longer a Haupt module. So you're kind of out of options. And this is very strange. So what this indicates is that those classic techniques that Ramanujan and Watson developed do not work here. It's still a genus zero surface. You would still expect it to be a relatively simple, to have a relatively simple method of proof, but the standard methods don't work, which is very peculiar. So, okay, let's try a second attempt. Now, one thing you can tell by looking at this fairly quickly, you can tell from the freshman's dream, for example, this x is 1 mod 5. So I can write x as 1 plus 5y, and y is a modular function with an integer power series. And in fact, y has a very nice eta quotient form. It's this form here. Perhaps might be a bit more promising. Now, notice something. X is still an eta quotient, so that means 1 plus 5y is an eta quotient. So if I divide by 1 plus 5y, what I get is still an integer power series in Q. Okay. So this y, so I can write x in terms of y. The problem is that y does not have zeros all the poles of L1 over F. So I can't just multiply L1 over F by a massive enough power of y to overpower all the poles. But I can multiply by high enough power of x, as we've already said. And a polynomial in x is going to be a polynomial in y, because x is 1 plus 5y. So I have L1 over F is in this ring, C of y x inverse. And let's see what that actually looks like. Right? So L1 looks like this. Again, this is Wang and Young's original form. And this is the form that I got. Now again, we don't have to worry about that F. And we don't have to worry about 1 over 1 plus 5y, because that's an eta quotient. It has an integer power series. We can ignore it. All we have to do is look at the polynomial that's left. And sure enough, 5, 5, 5, 5, 5. We have the divisibility by 5. It falls out very naturally as a result. And it's only a single variable identity. I can get similar identities for L2 and L3. As you would expect, they get big fast. But it's the same idea. You can still ultimately pull out the necessary powers of 5 that you need. And to my knowledge, and if one of you guys know a counterexample, let me know. But to my knowledge, this is the first time that I've seen these kinds of identities where in a sense you're working over a localized ring instead of a polynomial ring in X. Even in the more advanced kinds of proofs for partition congruence families, say when you're working over higher genus, for example, or you're working in cases where you don't have piecewise L-adic convergence, so like the Andrew-Sellers problem, or even problems where you don't have a very nice eta quotient representation, like the classic problem for powers of 11. In all these cases, you're still ultimately working either with CX or with a free CX module. I was able to come up with a proof for the divisibility of these Cn functions that does not use this very nice structure. Instead, it has a slightly modified structure. I can show that L alpha divided by 5 to the alpha f is the localization of zy at s, and s is just the non-negative powers of 1 plus 5y. That is, I'll call it the weak result, just because it gives you a neat conceptual idea. But I can do a bit stronger. I can tell you what the power is that you need to push everything up into the polynomial ring. So it's just this little floor function plus 1. that will push each L alpha up into just your regular polynomial ring for Zy. And it obviously doesn't affect divisibility by 5. I am unaware of this kind of technique being used anywhere else. I think the reason is it looks scary, because when you go back here a bit, see, look at this L1. If I want to design a way of proving this kind of congruence family, I'm going to have to work with a sequence of linear operators, so U operators. And each of those operators is going to have to work on a fraction, a power of y divided by a power of 1 plus 5y. And that looks scary. It looks extremely detailed and intimidating. It turns out it's not that, well, it's not that bad. It's a little tedious, but it can be done. And the result is very elegant, I think. And let's see, how much time do I have left? 6:32, so we still got a little time. So I think I will skip to the computational considerations first, and then maybe if we have time, I'll go into some of the details. But the idea here, and I'll at least stick to this slide for a moment here, is to show that each L alpha, when you divide out by f and the necessary power of 5, you can write in this kind of form here. So m greater than or equal to 1. This is finite. Okay, so it's not an infinite series. Sm 5 to a certain power, y to the m over 1 plus 5y to the n. And the idea is you apply an appropriate U operator, and what you get is a large mess of objects. And you reorganize everything, and the net power of 5 is 1 more than what you want. So you very, very carefully design space, and you define this mu of m very, very carefully. And I think I'll skip this for the time being. I may come back to us if we have a little bit of time. It gets complicated, but I don't want to. Here's what I want to focus on for now. One more additional thing that's kind of interesting. So Wang and Yang's proof, as I say, work with a rank 2 free ZX module. And they work with a modular function that has a degree 5 modular equation. Okay. Now what that means ultimately, and they have an alternating series of U operators, when you put all this together, it means that they need to prove, in order for their total induction to work, they need to prove a total of 20 initial relations to make this work. And again, that's what you would expect over a genus 1 surface. All of the things the same. But we're working over a genus 1 surface. So using the same technique, you would expect 10 relations. So how many relations are needed for this kind of proof that I've set up when you're working over this localized ring? Well, we have a degree 5 modular equation for y, and we have a degree 5 modular equation for 1 plus 5y. That can be, we can get those without too much trouble. So right away, you're working with a top and a bottom, and you would expect 25 initial relations for each U operator that you're working with. So here I'm working with a U operator, Ui, and I will be 0 and 1, say. So I have 2 different operators. So I've got 2 different operators and 25 initial relations. So you would expect me to have to prove 50 initial relations on how these U operators act on these fractions, y to the m over 1 plus 5y at the n. And Wang and Yang only need 20, because this doesn't look like an improvement in that respect. However, I want you to notice something here. I can write everything here in terms of x, where x is 1 plus 5y. So if I write everything in terms of x, right, knowing that this u function is a linear operator, so for example, I get a 1 over 5 to the m, I can just pull that out. And I can expand this out as a binomial sequence. That's not a big deal, right? So I can write this in terms of just u of 1 plus 5y to a power, in this case r minus n. And notice I have a modular equation for 1 plus 5y. So I can construct a recurrence equation for how to get these ui's of 1 plus 5y. But I'm not done. If I'm working with positive powers, I can write obviously this. I can expand this out, binomial sequence, and I can get everything in terms of my u operators applied to just powers of y. and I have a degree 5 modular equation for powers of y. So I can put everything backwards. If I have 10 relations, so and by relation I mean a very explicit representation for ui of y to the k in terms of powers of y and 1 over 1 plus 5y. Then I can put, and I have, say, 5 relations for 5 consecutive values of k here. Then I have a recurrence relation. I can figure out how ui of y to the k looks for any k, positive or negative. Using that, I can use this formula here to figure out ui of 1 plus 5y to the n for non-negative n. I do that for 5 consecutive powers, then I can get a general relationship because it has a modular equation. And I work my way back up. And I can, in fact, get all of the 50 relations that I need. So the proof I need requires 50 relations, 50 initial relations. But these relations are algebraically dependent on each other, and we can break it all down to a total of 10 initial relations. So 50 in practice, but 10 in principle. So at least in theory, it's still an improvement on the work of Wang and Yang. This, again, is very, very interesting. You still see some of the hints of the genus being 0. The genus being 0 sort of predicts that you have this at most 10 initial relations to get your induction argument started. And it turns out you can get it down to 10. And I put this paper out last March or April, and I have a mathematical notebook attached to this where I go through all these calculations. It's a little tedious, but it can be done. How are we doing? Any questions? I know it's a lot of stuff, and I've skipped over the actual proof, but the proof is a bit detailed, and I still got 20 minutes. I may come back to it in a minute. But here are just a summary of the key things that I want to focus on. So Wang and Yang, they gave a proof for this sequence Cn, for this congruence family. They use techniques for handling congruences when the associated Riemann surface has genus 1, and it doesn't, it has genus 0. So one would expect the traditional genus 0 techniques would work, and they don't. So this new approach uses only one modular function instead of 2. So if you like, it's a one variable proof, because each of these identities you can express for each L are just identities in terms of a single function. We require 50 initial relations to sort of get the induction argument of the overall proof started, but they're algebraically dependent. They reduce to 10 cases. This is in contrast to the 20 that Wang and Yang need. We have this neat localized polynomial ring. It's a neat structure that, again, I think is not only unique, but I have a suspicion it can be used in other places. I've actually started looking at a few other problems that might be amenable to this technique. And finally, there's one additional very interesting problem. So there are several problems that can hit you when you start working with these sorts of congruence families. The genus of the underlying modular curve plays a role, as you've seen. Also, how you can represent the modular functions involved becomes an issue. Ideally, you'd like them all to be represented as eta quotients, but very, very nice eta quotients. So for example, if I'm working over x07, gamma 07, I want to write all my functions in terms of eta tau and eta 7 tau, preferably in some nice quotient form, or combinations of objects like that. You may know over gamma 011 that doesn't work. This is one more reason that the partition congruences for powers of 11 is so hard to solve. So there's a representation problem, there's a genus problem. There's also a much more technical problem that's difficult to explain. This has come up with the proof of the Andrew-Sellers conjecture, where you take an arbitrary function in a sense, an arbitrary modular function, and you apply an appropriate sequence of U operators. For for example, for gamma 0, 5, or 7, or 11, when you apply a certain sequence of U operators, you're going to pick up a power of the primes that you ultimately want. So for gamma 0, 5, you're going to keep picking up powers of 5, or powers of 7, or powers of 11. It's just a matter of bookkeeping to make sure that they come up in exactly the way that you want them. In the case of the Andrews-Sellers congruence family, it was proposed, I think, in 1994. It wasn't proved until 2012. One of the reasons it took so long to prove is that this is no longer true. That when you take a function in the space that you want, you apply an appropriate U sequence over and over and over again, you won't end up getting higher and higher divisibility by a power of the prime that you want. In this case, the power is 5. And this is one of the things that makes proving this so difficult. And you have to it's a bit more difficult. Professor Paula and Sylvia had to work with a pair of rank 2 ZX modules, even though in principle you only need one. They had to work with 2 of them, and they had to bounce back and forth as you apply various U operators. So the issue is L-adic convergence, in a sense. You want to be able to gain powers of 5 in each step. So there's one more really interesting peculiarity here. If I go from L alpha to L alpha plus 1, I have to always pick up an extra power of 5 when I apply the U operator. And that is indeed true, but using this localization technique is not obvious. And there are 1 or 2 spots where it looks like it doesn't happen. And that is very, very strange. I had worked through most of this proof in December of last year, and I had found a small mistake, and I had to actually go back over it. But when you go from L alpha to L alpha plus 1, you pick up an extra power of 5, but each component of your function will not necessarily pick up a power of 5. There are certain functions that you have to actually add together to produce a power of 5, and that gets really, really tricky and really, really scary. And I've got 15 minutes. I may go over this very, very briefly, although I don't have that much time, and I don't want to confuse you guys too much. I think I've already done enough confusing. So before I do, how's everybody feeling? Is everyone all right? Okay. So let's see. I want to, you know what? I don't think I want to prove. If any of you guys are interested, I'll show you a little bit later. But the thing is, it gets complicated really, really fast. You may notice here. So here's the general theorem of what these U operators look like. You don't have to worry about what U operators exactly look like here. You don't have to worry about them too much for the time being. But you have the typical components of each of your identities are going to be a power of y divided by 1 plus 5y to a power. And when you apply these U operators, you get these neat polynomials here. These are finite sums. This h1, this h0, these are integers. I get a certain power of 5 tacked on. And then I have y to a power over 1 plus 5y to a power. Relatively straightforward. And you may notice this pi 1 and this pi 0, they look complicated. They look really complicated. There's a reason they look this complicated, because it took weeks and weeks of very careful bookkeeping to get these powers to work properly. And the idea is, if I say define 2 spaces of functions, I'll call maybe Zn and Vn, and define these kinds of spaces in terms of what the power of 5 is for each coefficient of y to the m. So I have a series Sm 5 to the theta m, y to the m over 1 plus 5y to some n. And theta m looks like this here. And phi m looks like this here. It looks almost exactly the same. These are the spaces that I kind of want to bounce back and forth in. My odd index L alphas are going to be in here. And when I apply the appropriate operator, it'll turn into an even index L alpha, and it'll be in here. And when I do that, I want to pick up an extra power of 5. And then when I apply again, I want to pick up an extra power of 5, and I want to keep on going. So the idea is I want to show that 1 over 5FL1 is in Z3. Then I want to show if I have any F in Zn, then 1 over 5U1 is going to send it into V5n minus 4. And then any F in the Vn, I divide by 5 and take the U0 operator, it will send me into Z5n minus 2. And I can keep on going. Each time I go, I pick up an extra power of 5. These SMs, I should say, are integers, right? So I pick up an extra power of 5 at each step. So it looks sort of like this, and I won't go into too much. But for example, going from even to odd index, I take an f in Vn. This might be L2 or L4 or L6, an even index L. Then U0 of f is going to break apart. So it'll be U0 of this, and U0 is linear. So I can break this sum out, and I can break the SM and the power of 5 out. So it's just U0 of this. And I have an expression for this in terms of some auxiliary, H0, and a sum in terms of R. Looks really, really scary, right? But ultimately, I've got these powers, this power of 5, phi of m plus pi 0 of mr. And I'm starting with phi of m, and I'm going to theta m, right? And I want to pick up an extra power of 5. So all that 5 business I want to show is greater than or equal to theta m plus 1. So 5m plus pi 0 of mr is greater than or equal to theta r plus 1. So I gain an extra power of 5, and I can pull that 5 out. It turns out I can't do this. This looks horrid and scary, but it can be done, where I can show that I get an extra power of 5 at each step. And this is fairly typical of this sort of proof for congruence families. Okay, you don't have this rational polynomial, you just have monomials, but it's still the same idea. Problem is, odd even index, if I try the same thing, so f and z, and so I might have L1 or L3 or L5, and I apply my U1 operator, right? Then I'm looking at U1 of ym over 1 plus 5y to the n. And I get this lovely combination. And again, I would like each piece in this sum to increase in its power of 5. I would like theta m plus pi 1 of mr to be, well, I'm going into phi of r this time. I want it to be phi of r plus 1 at least. I gain an extra power of 5. So I'm bouncing back and forth between these spaces, and each time I do, I pick up an extra power of 5. That's the idea. So that's what you want to prove. You want to prove these here. So I have expressions for phi, theta, pi 0, and pi 1, and I want to prove these inequalities. And I can't do it. And this is where the real bizarre thing comes in handy. The first inequality I can prove. The second one I can't. Second one's wrong. So theta m plus pi 1 of mr is not necessarily phi of r plus 1 at least. Sometimes it just comes out as 0. Now, the way that is resolved, and I will leave it here because I got 10 more minutes, but it would just take too long, and I think it's already getting really confusing. But the idea is I need to show that several of these terms, so, you know, it's like y to the r here, say y to the 1, okay? I'm going to have several values of m that will contribute to y to the 1 here. And I need to show that those values will all add up to gain an extra power of 5. And what that ultimately ends up doing is that means I've got to show that this whole sum comes up divisible by 5. So like here, the coefficient of y to the 1 over 1 plus 5y to the 5n minus 4 has this form here. And for large enough m, for m equal 4 or 5, I pick up the extra power of 5 I need. I don't have to worry. So I can reduce this mod 5 to these first 3 terms. And it turns out these auxiliary terms, h1, I know the arithmetic properties of these. It took me weeks to figure these arithmetic properties out. But rest assured what this means, look on bottom, for example, h1 of mn1 is 1 mod 5. So I can take this sum here, and this is just congruent to the sum of Sm mod 5 for the first 3 Sm. And if I look at L1 as an example, so S1 is 24, S2 is 361, S3 is 2410. And you'll notice the 3 of them add together to produce a multiple of 5. I mean, it's obvious, right? Like the third one's divisible by 5. These first 2 add up to be a multiple of 5, right? But I can't prove that S of 3 always comes up with an extra power of 5 in. It won't work. In fact, if you look at L3, this is not divisible by 5, and this is not divisible by 5, but this is. So S1 is not divisible by 5, and S3 is not divisible by 5, but S2 is. That's when you divide through by the necessary powers of 5. So you have to prove that you have to start with the assumption that these first three terms will add together to produce a power of 5, and then you can produce an induction argument. So L1, when I divide out the 5 that I need, these first three components will sum to a multiple of 5. And I can prove with a very tedious induction argument that the same will be true for L3. L3, I'll have a 5 to the third here, because L3 is divisible by 5 to the third. But when I pull that 5 to the third out, what's left here, these three terms will add up to a multiple of 5. And then the same is true for L5 and L7. I can get an induction argument going, and then we can finally state the whole proof. This is also something I'm not familiar with from any area of partition congruence families. We have this really peculiarity in proving the phi-vatic convergence, where you are basically forced to study these auxiliary terms and their arithmetic properties and show that they sum together in the right way to get a power of 5. And this is not an easy thing to prove. So I think I will leave that here because it gets complicated, as I say. So, and the general method, I think I'll skip for just the time being. Although if you guys have interest, just let me know. The big thing is, I think this method has a large amount of potential because it shows that the original techniques don't work. Even when you stick to a genus 0 surface, the original techniques just aren't enough. And that is weird. And I have a suspicion I know roughly when the original techniques fail and when they don't. And it has to do with computing the space of eta quotients for gamma 0 in, particularly when the genus is 0. And whenever the space of eta quotients is non-trivial, you immediately have something interesting to look at. Whenever you have a congruence family associated with that congruence subgroup, then I think that this method might have a bit of potential. Again, as I say, it's never been studied. I'm amused by this. This is an empty bullet point, but still kind of neat. So this result uses some arithmetic techniques, some algebraic techniques, some analysis, some topology, some computational stuff, a lot of experimental stuff. So it's a neat combination of all these results. And again, I suspect this method can be modified actually for all families of congruences, but for a lot of cases like gamma 0, 5, you can show this basically reduces to the technique that Ramanujan and Watson do. You won't really get these localized sets, or if you do, they'll just simplify into just the regular polynomial ring. But there are cases where it may not. And in particular, when you're looking at partition analogues of Mach theta functions, I think that's when a lot of interesting results come up. I need more examples, though. Now, in fairness, I spent the last few months putting together my thesis and job applications and other things, so I haven't had much time for math. But I'm starting to look back up at these. And if anyone has any pathological congruence families, ones that you're having trouble proving, or you're proving in some really convoluted way, especially when it's associated with a genus 0 surface, feel free to let me know. I would be very interested. And I'm working on a research proposal to study this method. Hint, hint, if anyone's interested. Actually, I've already worked on it. I've submitted it to the FWF here in Austria. I expect a rejection letter any day now, but who knows? And let's see, that's, yeah, 5 minutes left. That's a good place to stop. So that's it.
All right.
Thank you. Okay, great. Let's thank Nicolas for his talk. I guess we can virtually clap or clap in person. This. Great. Do we have any questions?
Yeah, I have a question. So Nicolas, in the highlights of the proof, you were talking about these two operators that you kind of alternately apply. And just thinking about the structure, it just reminded me a lot of what went into the proof of, Folsom, Kent, and Ono's paper on the fractal partition function properties. fractal properties of the partition function.
I know about this paper.
We
I've not looked at it very closely, although it looks like a lot of fun to read.
Yeah, they kind of have the same thing where these two operators, and you kind of alternate applying these two different operators to get some structure. And there's also an appendix of that paper talking about kind of the general chaotic picture going on there, which was written by someone else. Maybe it was Caligari, maybe someone else. Anyway, it just reminded me of that. So I wonder, you know, it just might be interesting to look at that and see if there's some similarity or if there's some fractal properties in these other cases as well. And it just really reminded me of it. So yeah.
It's a good excuse to look over that paper because I've wanted to for a while. I should say the alternating U operator thing, that's common to pretty much every proof of congruence families that I know, where you have two of them, right? Where your U1 is just the regular U5 operator and U0 is U5 operator, but with this little prefactor in. Like I have this eta quotient Z in here. And I'd go actually a little bit further here for technical reasons. I have that 1 over F just to simplify matters. But so that specific bit is common to a good deal of the subject. But yeah, I'm guessing that paper gives it a bit of context and why that's so useful.
Yeah.
Excellent.
Well, and that paper has been generalized to a few other specific situations by the same method of proof, mainly by some students, but to my knowledge, I'm not sure much has been done with the more explicit meaning behind the structure. Other than that, it's a phenomenon you can prove in a few cases. Yeah.
Thank you.
Great. Any other questions or comments?
Oh, there are some things in the chat. I can't see the chat. Hang on, I'm going to stop the share. If you guys want to see the screen again, just let me know. Now I can see the chat.
Yeah, there's a question in the chat about Ramanujan congruences for powers of 13 since x013 has genus 0.
Ah, yes. So, but that's not that same really nice congruence family, is it? I mean, do we have a really nice simple congruence family for powers of 13?
No, but for maybe he means for SPE or something like that, simple or some other function.
In that case, yes. It's actually here. I can look. I can do this fairly quickly. Give me a second. Bring up my old. I should have had my Mathematica stuff open.
So I guess maybe I have a follow-up question that kind of ties into this.
Please.
So this method of looking at the polynomial rings, like you show that if you choose something that you don't necessarily see the congruences like visually, like you can get these rational numbers as coefficients. So is this method useful at all for like detecting congruences, or is it mostly useful for if we suspect or like see that they're there for proving them?
So I've got techniques for actually seeing them, like in, or actually, if you want to know, this originally came up. I originally worked with this technique, or developed it out of doing some experimental work with Silvio Radu. I work with them a lot directly at risk here, and we developed a lot of experimental techniques. Where basically, you can imagine working with just that x, that function x. Power of x writing as a combination of x's. Or when the genus is higher, it's the same idea, like you're dealing with a zx module of a certain rank, and you're just dividing through, and you have something that is roughly stable under repeated applications of a U operator. You have problems with things like L-adic convergence, especially when the genus gets high and you're dealing with all sorts of different modular curves. But it's a very useful algorithmic technique for checking a large number of cases. And then you can check for divisibility. In fact, this is how a problem I did a couple of years back, where Choi Kim and Lovejoy gave this really neat, they conjectured a congruence family associated with the Rogers-Ramanujan subpartition function. And, but they didn't say what the exact form of the congruence family was. And we used this congruence testing technique to work out what the congruence family was, and then we were able to prove it later. Sylvia and I were able to put a paper out. It's in the journal Symbolic Computation. I remember, I think Dr. Raum said something about Sylvia a couple weeks back, and I do apologize for not being at his talk because I saw it on YouTube. It was an excellent talk. And I forget exactly what he said about Sylvia, but Sylvia's techniques are very, I think delicate was the word, like they're extremely detailed. And that sometimes has value. And this is one of those cases where it has value, where he's not afraid of doing a lot of tedious computations, and developing this algorithmic machinery is very useful. And speaking of algorithmic machinery, I just did the computation here. The eta quotients for gamma 0, 13 are trivial. So I expect you wouldn't have to bother with this localization technique. The standard Ramanujan-Watson technique should work in that case. So a problem would be in places like, here I can do a couple of examples here. So gamma 0, 10 is an example where you get multiple Haupt modules. In fact, you get 3 of them. That might be a problem, for example. Or what's another good example? I don't know what the next genus 0 one is. I should. 16? Yeah, gamma 0, 16 might. So if you work with any congruence families and it's associated with gamma 0, 16, that suggests you might have an interesting problem. So it depends. If you have more than one Haupt module eta quotient, that especially suggests something interesting is happening. So that's an answer to the question in the chat.
Yeah, I think there's a follow-up to that where they suggest, maybe there's not something where the partition 0 mod powers of 13, but there's another family of modular forms that it would be congruent to. And I think that in the paper Larry mentioned that Ono and them also do this, where I think it's like almost an intermediary step between showing some of these congruences that they show. If you apply this UP operator, you can get a congruence to another modular form, and then it becomes something easier to work with. So I think what's being suggested in the chat is probably true.
Is the natural congruence between modular forms in this case? Yeah, that would be interesting. Do you know what that paper is?
Larry, what is it called?
Oh, something with the word fractal. Or, well, that might not be in the title.
Can try and search.
It's called L-adic property of the partition function.
Yeah.
I heard L-adic.
Yeah, something like L-adic properties of the partition function.
Okay.
And they write it down generally for like each specific L, and then you can specialize for like L 5, 7, and 11. You get something really nice that you can show a 0. And this is where this is the same paper, right, where they show congruences for larger primes, but they get more complicated looking than the nice Ramanujan type ones, right?
Yeah, I guess that should fall. I mean, Ken showed that before this paper, but yeah, okay. It shows you still, for any prime, you still get something relatively nice, something that they call fractal behavior. And for 5, 7, and 11, it's the actual Ramanujan type congruences, but for other primes, you still get something. Yeah, but in particular, it implies there's interesting examples of congruences mod other primes too. So actually, they do mention 13 as an example. So there's a congruence of where the common differences are 13 cubed to 6 times partitions of 13 and plus 6 that comes out of their theory. So there's sort of self-similarity structure of partitions on certain progressions mod 13. Even though you don't get the Ramanujan congruence stuff, you still get some congruences. They just don't happen to be congruent to 0 or something. They're congruent to other partition numbers mod 13.
Yeah, can I say something?
Please.
Yeah, this result you're talking about, 13, is actually due to Akin and O'Brien in 1967, where they proved what you're saying, Larry, where there's a congruence for powers of 13, but it's between the L alpha and the L alpha plus 2 coefficients.
Hmm.
So that,
Okay.
and that, they also did the same thing for the coefficients of the J function as well. So another thing you could look
Okay.
at, Nicholas, is try to look at, so even though there may be not a congruence mods for powers of 7 for the SPT omega function, maybe there's something mod 7 to do with like the Atkin-O'Brien, where you're going from alpha to alpha plus 2 and look at the coefficients between the two functions there and see. And also, yeah, I mean, that was, in the Ono paper, they do touch that, but that was also, that goes back to Atkin-O'Brien's paper of 1967. It's a very nice paper to read. But anyway.
Excellent.
That's all I
Thank you.
wanted to say.
Thanks for that.
Well,
Thanks.
that's useful. I do enjoy Atkin's older paper for powers of 11. I haven't looked at his paper for powers of 13. I know he's done a lot of work in the J invariant. So I'll give his work. I'll give his work a look too.
Yeah, thanks, Frank. I see that Atkin and O'Brien's work is cited in the Folsom Kenton Ono paper, but not until a little bit later. But they say that their theorem is inspired by that earlier work.
Yeah,
Yeah.
well, that's great.
But I just saw the 13 example, and it doesn't right away mention it there, but then it does on the next page or something. Yeah.
That means you have to read the whole paper before you find stuff.
Well, I'll start with Atkin and O'Brien's paper, and I'll work my way up. But it's
There's actually 3 cited here. There's Atkin, and then Atkin O'Brien. But there's only one joint one, I guess.